So, good morning, everyone. As you noticed, we have some changes in the schedule due to some technical reasons. And today we will have two lectures. The first will be on pyrochemical processing, or let's say non-aqueous methods for reprocessing of spent nuclear fuel. And the main method that is more developed than others, it is pyrochemical reprocessing or pyroprocessing of the spent nuclear fuel. Yep. So, in principle, non-aqueous methods for the spent nuclear fuel reprocessing or other nuclear applications, it is use of the molten salts, or it can be gas technology based on different volatility of the fluorides of the elements of actinides and fission products. It is supercritical extraction or supercritical fluid extraction, for example, in carbon dioxide, but not only, of course. And it is use of ionic liquids. So it is not aqueous solution, it is some organic solution, or as we will see, at high temperatures, molten salts, they're also ionic liquids. Yeah? And these methods, they can be used for reprocessing of spent nuclear fuel that we will see today, for fractionation of high-level waste, or for other metals, refining, purification. Molten salts, they can be used as a liquid fuel. Yeah, and on Tuesday, it will be a lecture about the molten salt reactor. So you will see how it works and what is the basis for that. Or molten salts, they can be used as a heat carrier or heat transfer medium in the reactor. Yeah, and generally for reprocessing of spent nuclear fuel, we can use as a solvents. Normally it is molten salts with the composition of the, so it's a mixture of the chlorides of the alkaline or alkaline earth metals, or it can be even pure lithium chloride, for example, as a molten salts. And as working cathodes, for example, it can be used molten metals like cadmium, bismuth, or others. And the applications of the molten salts and electrochemistry at high temperatures started actually quite a long time ago. Already in the 50s, it was ideas to use these methods for nuclear fuel reprocessing, because generally these electro-refining methods, they're widely used in normal hydrometallurgy, for example, for copper refining, for copper purification. There is a use of this electrolysis in melts. And so the idea was to use the same methods for the reprocessing of spent nuclear fuel. And it started mainly in the United States first, in Argonne National Lab, and later was developed in Soviet Union, in Korea, in Czech Republic, in Japan, in India, and now in China. Why these methods are has so much interest for the sciences, for the technologists, maybe mainly, because the main advantage of these systems, molten salts, is their high radiation stability. There is no water, yeah, so there is no radiolysis. Molten salts, they're already in ionic forms. It is cations and anions. so there is nothing to be destroyed. They're already in the separated forms, let's say. There is no light atoms like hydrogen and carbon. That means that there is no probability for criticality. That means that we can use very high concentration of the fissile materials with no danger of the chain reaction, nuclear chain reaction, like in water. Yeah, you know that in water there is restrictions to use high concentration of plutonium because the chain reaction can occur due to the moderation of neutrons by hydrogen atoms in water, and thus these thermal neutrons can result in the production of this chain reaction. In molten salts, it is not so probable, so that's why the concentrations, the working concentrations, can be much higher, and that means that you can make equipment much smaller, more compacted. Yeah, you need less space than for conventional hydrometallurgical operations using aqueous solution and organic solution. And as far as there is no danger about radiolysis, so there is no water, that means that there is no production of hydrogen, flammable, explosive hydrogen. That means that we can use the spent nuclear fuel directly from the reactor. Maybe not directly, maybe after short period of storage. Maybe 1 year is enough to store the spent nuclear fuel to be able to work with this material with the pyrochemical processing. Because in aqueous solution, it is not possible. The radiation is too high and the radiolysis is too intensive in aqueous solution. But in molten salts, it is not a problem. So from economical point of view, it is very good because if you store spent nuclear fuel, you pay money for storage. Yeah. Also, during the storage of spent nuclear fuel, there is additional accumulation of americium, for example, due to the decay of plutonium-241 that is present in the spent nuclear fuel. So during accumulation of spent nuclear fuel, there is accumulation of minor actinides, and the idea of the reprocessing of spent nuclear fuel to remove minor actinides, and during the storage they accumulated. So the shorter the period of storage, the lower will be the concentration of the minor actinides. So it is another advantage of the pyrochemical process. So short period of time of storage of spent nuclear fuel, very high concentrations that can be reached. There is no danger of the formation of the precipitates because there is no this countercurrent flows of the between the equipment, so there is no danger of the formation of the precipitates like we discussed for Purex process or other process. So there are a lot of advantages of this processes. And these molten salt technologies, as we already discussed, they can be used for many applications, and for us it is these two applications, electrorefining and electrowinning, is one of the most important. So why it is possible? Because all these separations, they are based on different electrochemical properties of the metals in molten salts. In water, of course, they also have different properties. But in molten salts, you can see that uranium and plutonium can be easily separated from the fission products, yeah, by application of the certain potential to the electrodes. So, how to make this formation of the metals? There is different ways. One of the way to separate metals and from each other. It is use of the let's say solvent extraction, not solvent extraction, but in electrochemical fashion. Let's say here it is a liquid metal that is cathode, and the molten salt. Yeah, so there are two liquids. It's not maybe very easy to take maybe to adopt it in the mind, because usually when we talk about the extraction, it is aqueous and organic solutions, but here it is molten salt that is liquid, and the liquid cathode, it may be cadmium or bismuth, yeah, and there is reactions between these two liquids when metal or our uranium is redistributed between these two liquids. And by the applying or the certain potential, we can make it possible for different metals. Yeah, we can extract uranium, we can extract plutonium, or we can extract, for example, noble metals, depending on what we would like to separate. How to produce metal fuels, as we are using mostly dioxide fuel, uranium dioxide, or MOX fuel, or that is also uranium plutonium dioxide fuel. To do this, there is a possibility to use an electrochemical reduction or metallization process. It is known that uranium dioxide and plutonium dioxide, other actinide dioxide materials, they behave like metals in molten salts. They can be easy, they have a high conductivity, and they can be transferred. We can see it later to the anode. But here there is a direct reduction of uranium dioxide with the application. So this basket, it is the cathode basket. So there is a reduction of the uranium. You can see, probably, I hope you can see that these pellets, they are placed, that there is a contact between every pellet. Yeah, so it's a very dense placement of this uranium dioxide pellets. As far as there is contact between them, and there is a high conductivity of uranium dioxide, the process of metallization goes very efficiently. So, and here is an example, as I remember, from Korean example. So after 9 hours, there is a total metallization of the uranium dioxide. Or we can use a transport of the actinides. Again, actinides soluble in these molten salts in different forms, not only in forms of the, let's say, pure cations like uranium +3, plutonium +3, or +4. They are also soluble in the form of the dioxocations, yeah, like uranyl cation or plutonyl cation, uranium O2 to plus, or plutonium O2 to plus. They're also soluble in these conditions, and they can be transported to the cathodes. But in this case, when we don't have oxygen, we don't add oxygen, and it is a metallic form of the uranium or plutonium. The oxidation states is +3 or +4, and on the cathode, on the solid cathode, we obtained uranium dendrites, pure uranium dendrites, and in a liquid cathode, it is a mixture of minor actinides, uranium, and plutonium. And this is a general scheme, one of the combination of the different processes. This was supposed to be used in Russian facility. So the first step is the fragmentation of the spent nuclear fuel by chopping or by Yeah.
Yes, sir, actually, I was wondering that. Uh, uh, so I was just wondering that, with all these processes that are aimed at spent fuel and the reprocessing, but can these also be used to say, the cladding material? Because when you look at zircaloy, the purification of zirconium from its ore and separation of hafnium is a very costly process. And once it is in the reactor and when you take it out, the cladding material is not so much damaged. Like there could be some mechanical stress strain or some cracking, but the purity of the metal is more or less the same. So can we use these methods to extract the metal again from the?
Yeah, there are projects on this topic. The main problem with the cladding material is the presence of neoprene.
After.
Isotopes,
Oh, separate.
That's zirconium, even if it also contains zirconium radioactive isotopes, but their zirconium 93, if I remember correctly, it is long-lived and only pure ether emitter, so it is very low radiation from
the
irradiated zirconium
yeah.
itself. So if we, but niobium has high energy emitter radiation and some ground. Correct. So if we remove niobium from zirconium, we can use it.
I reuse it.
There are a few projects on this topic also. This pilot.
I see. Okay. Thank you.
Any more questions? Yeah.
Thank you for your presentation. I just wanted to ask, are these processes used in Russia for a chemical process?
Yes.
And what are the restrictions and limits for using them? Can we use it for any types of?
It's just the technical limitations. For example, this inner chamber, the first constructions were not very hermetic, for example. Yeah? So some oxygen, so it was some penetration of oxygen inside the camera, and it was not possible to use it. So it is a lot of this technical, the construction materials, they are not the stainless steel materials, they are also not very stable. So there is a development of new construction materials. So in principle, the technology is working. But to make it in industrial scale, there are these technical problems that must be solved. But, yeah. So that's the main drawback or limitation of the technology. All the chemistry are known, so everything is clear how to make it. But the construction materials, these inner chambers, inner pipelines, that's the main limitations.
Okay, thank you.
Any more questions, comments from Kazakhstan? No.
Thank you for the nice presentation. This is just something that I didn't understand. In some places, instead of SNF for spent nuclear fuel, it was THM. What does it stand for exactly?
It's just tons of heavy metals. It's a
Tons.
radiation that is used everywhere. So because initially we again take uranium dioxide only, and all the calculations are made on uranium and plutonium, so DMS. Okay, so that's tons of heavy metals.
Can I have the question? You know that vacuum is very special environment. So can we use the vacuum to encapsulation of radioactive waste? Vacuum. Yeah. Yeah.
My answer is no, because there is no technique that will allow this vacuum for a very long time.
Mm.
Any material has some diffusion coefficients for air, and sooner or later it will be not a vacuum inside the capsule, but something gaseous atmosphere. And also these materials, they are encapsulated in, for example, the easiest way, they're encapsulated in stainless steel containers that must be resistant to the action of water. So all these matrix, canister, overpacking, their main goal, their main requirement is to prevent the contact of groundwater with the radioactive material. It is not very probable scenario when groundwater will come to the radioactive waste, but it is assumed as a forced scenario. Something's happened, some geological changes in this site, and water will introduce it in the repository and will interact with all the materials. And the main requirement for all these engineered barriers to be resistant to water, to protect the radioactive materials. And vacuum, there is no need for vacuum actually, because there is no problems with the interaction of the air. But if you are talking about the media for reprocessing, I use vacuum, but use inert gases, for example. First, it is much more easier. You can make a higher pressure inside the chamber, and it will avoid the penetration of air inside the chamber. So you make overpressure, and it makes it less probable, at least, for air to come to the chamber. If you have vacuum inside chamber, it's vice versa. Air will go in the chamber. It will be some cracks or some problems in the material. So that's why there's a need to use this over pressure inside the chamber. And first, and the second, the purging of the inert gas helps to mix all these solutions inside the units. So there is not a mechanical steering, but the mixing with the bubbles. So to avoid any mechanical parts, because mechanical parts can be damaged, and it is always better to avoid any mechanical frictions, movements inside radioactive solutions. Any more questions? If not, then thank you.
Да, здравствуйте.
Можно чуть-чуть вот добавить громкость.
Здравствуйте. Нормально.
Наставник отвечает.
Hey, dear colleagues, please take your seats. And now we are going to have our second lecture. Alexey Konoplov is our colleague from Geography Department. And you can see that he is working both in our Moscow State University and in the Institute of Environmental Radioactivity in Fukushima University. So please, Alexey, thank you.
Раз, два, три. Что-нибудь слышно? Все нормально? Хорошо. Sorry about that. So, technical problem. Yeah. This is another important report, also quite recently published. And this is already 23 years ago. US document, technical study of spent fuel pool accident risk at decommissioning nuclear power plants. So, but as I told you already, all the modeling and calculations of hypothetical spent fuel accidents with spent nuclear fuel, they are based on the experience from real accidents. And actually, today I will tell you about this accident chronologically. So the first one was at Production Association Mayak in Russia now, in Soviet Union at that time. So we will consider this in more details. Then the most severe accident at Chernobyl nuclear power plant, which happened in April 1986. And then the Fukushima Daiichi nuclear power plant. Daiichi means one. So Fukushima Daiichi means Fukushima 1. This is because in Fukushima prefecture, there are two nuclear power plants, Fukushima Daiichi and Fukushima Daini, which means Fukushima 2. Fukushima Daini was not damaged as a result of tsunami, but the accident was on the nuclear power plant Fukushima Daiichi. So, IAEA, International Atomic Energy Agency, established the specific program devoted to the spent nuclear fuel potential accidents, their scenarios, modeling, and calculations. And important is that this program was based on Chernobyl accident, Fukushima accident, 3 Mile Island accident, and of course the experience from Mayak and Sellafield in UK. So this was a collaborative research project, management of severely damaged spent fuel and corium, which lasted from 2016 to 2022. Okay, few words about the Production Association Mayak. Mayak belongs to Russian State Corporation on Atomic Energy, Rosatom, and is located in the northern part of Chelyabinsk region, near the towns of Kyshtym and Kasly. The enterprise was established at the end of 1940s to produce and reprocess weapons-grade plutonium. This is detailed map of Mayak site. So you can see here, this red is the location of industrial site itself, where Mayak is. So then you can see the health protection zone, and observational zone. This is the health protection zone, and this is the observation zone. Okay. When we consider the MAYAC, we should take into account three major sources of radioactivity to the environment from MAYAC. First, this was direct discharge of intermediate and low-level radioactive waste to Teche River, which happened in 1949 to 1956. Then the discharges of liquid radioactive waste to Lake Karachay started from 1951. And then Kyshtym accident, so-called Kyshtym accident in 1957. I should mention that the Kyshtym town, which is located over here, has nothing to do with this accident. Actually, this was accident on the site of Mayak. So, first, radioactive contamination of Teche River. First of all, as I told already, the intermediate and low-level radioactive waste was directly discharged to Teche River, specifically in these two reservoirs, Reservoir 3 and Reservoir 4. However, just 2 years after starting this discharge, people realized that the downstream Teche River is heavily contaminated by radionuclides. And this is the threat for the people who is living on the Teche River, downstream Mayak. So in this case, Reservoir 3 and 4, they served as traps for the radionuclides because radionuclides deposited on the bottom, and in some extent this prevented the, let's say, transport of radionuclide along the river. However, the contamination of Teche River became a big problem and challenge. Therefore, it was decided to construct another reservoir, much bigger reservoir, Reservoir 10. So this dam was constructed to create this reservoir. And therefore, the trapping of radionuclides increased substantially after the construction of this Reservoir 10. This was done in 1956. So, but it was still not enough to prevent radionuclide migration through the Teche River. So in 1963, another reservoir was created. The dam 11 was constructed over here. And now we have two big reservoirs which serve as a traps for radionuclides, which were discharged in Teche River in the 50s years. Okay, here you can see the this is very important picture, which is demonstrating how the production association Mayak, influence on the water quality in Ob River basin. Because Mayak is located over here, and this Kecha River is a part of big Ob River basin, which ended at the Arctic Ocean. And here you can see that this is the concentration of strontium in logarithmic scale. And here you can see distance from the dam 11. I told you what is dam 11 is. So you can see very high concentration over here. And then the concentration is still high up to, let's say, 1,500 kilometers. 1,500 kilometers. This is the length of Japan. And the strontium, traces of strontium-90 go till 1,500 kilometers. And this is the survey of 2005. Now we have 20 years passed after this survey. So it's interesting to look what is the situation now. So I would expect something like this. So it's became longer, and there is some decrease on the top. Okay, this is the Lake Karachay. Lake Karachay was known as the most contaminated lake on the Earth. Lake Karachay is located on the site of Mayak, inside the industrial site, and therefore there was no any access to this lake, and a lot of radioactive materials were discharged over there. Then for many years it was a problem, and then the remediation program, the big remediation program was started and finished in 2015. So from 2015 there is no any more Lake Karachay. It is covered. However, the radioactivity is still there. It's just covered by the S. And this radionuclide, they migrate to the groundwater. And especially mobile radionuclide, such as strontium-90 and cobalt-60. Here you can see the Lake Karachay. And here you can see the isolines of strontium-90 and cobalt-60 in groundwater. And these radionuclides, of course, migrate with groundwater flow. And this is the real threat. And this problem is not solved yet. And so there is activity around this, but it's not solved yet. So it's still there. Although Karachay itself does not exist anymore. And the final source of radioactive contamination was a so-called Kyshtym accident. It was an explosion, thermal explosion of a tank containing high-level liquid radioactive waste, which occurred in September 1957, creating what has become known as the Kyshtym accident. So 740 petabecquerel was actually released during the accident, but 90% of this activity was deposited inside industrial site of Mayak. And 74 petabecquerel of radioactivity was released into the atmosphere and dispersed by the wind to form the East Ural radioactive trace of about 30 to 50 kilometers width and about 300 kilometers long in northeast direction from Mayak. You can see the trace over here. It's very narrow and long because we can consider that the release was actually immediate, very short time, and lasted very short time. Therefore, this this is just reflection of wind direction. The wind direction was like this, and actually trace just reflected the wind which we had at the moment of this explosion. Okay, main messages about Mayak and Kyshtym accident. Dispersal of radioactive materials from Mayak to the environment led to harmful effects on the environment itself, restriction on land application, relocation of inhabitants from a number of settlements, and observed health effects on human populations. The radionuclide of main concern is strontium-90, as it is remobilized from soil and sediments to much greater extent than cesium-137 and plutonium isotopes. Increased contamination of groundwater, in particular by strontium-90 and cobalt-60 from Lake Karachay, is of serious concern until now. To avoid the transport of contaminated water down the Teche River, huge reservoirs were constructed in 1956 to 1963. Rehabilitation program to fill in Lake Karachay has been completed in 2015. The surface area of the lake has been reduced until the zero in 2015. So now, Chernobyl accident. So Chernobyl accident happened in April 1986, and this is the most severe nuclear accident in the history. So here you can see the, let's say, data about activities, released activities during the accident. So 10 in 15 is called petabecquerel, yeah? So this is the activity of cesium-137, cesium-134, iodine-131, and strontium-90 and plutonium isotope. They were released into the atmosphere and transported over the long distances, especially cesium isotopes and iodine isotopes were transported for the long range, long distances, contaminating the whole Europe, actually. Yeah, you can see here the cesium-137 deposition over the Europe. You can see that many countries were contaminated, including Scandinavia, UK, Germany, Switzerland, Italy, and so on. So, major releases occurred over a period of 10 days, opposite to Kyshtym accident, where it was immediate. In case of Chernobyl, 10 days lasted the release. During this time, there were several changes in wind direction. And here you can see that during these 10 days, actually, this is the first plume. Then direction was here, then here, here, and here, and here. Actually, the wind turned for 360 degrees during these 10 days. And this is why the picture of contamination is so different from Kıştım. We should take into account two factors when we analyze the map of contamination. First, wind and atmospheric transport, and second, precipitation. Because when you have precipitation, wet deposition of radionuclides is much more efficient and faster than dry deposition. And therefore, the precipitation accelerates the washout of radionuclides from the atmosphere and sometimes create specific hotspots like Tula, aerial hotspot in Russia, or a hotspot in Germany and Austria and Italy, and even in UK. There is a hotspot which is actually explained by the precipitation during that days. So here you can see the map of contamination by strontium-90. This is strontium-90, and this is plutonium isotopes. So the circle is 30 kilometers zone around the Chernobyl nuclear power plant. You can see that most of strontium-90 is inside the 30 kilometers zone. There is some nearby, and there are some spots over here in Belarus. Concerning the plutonium isotopes, almost majority of plutonium was deposited in the 30 kilometers zone around the Chernobyl nuclear power plant. Why is the difference? Difference is explained by the difference in volatility of different elements. The most volatile elements is iodine, then this more or less semi-volatile are cesium isotopes, and strontium and plutonium, they are refractory elements. They do not evaporate even at high temperatures, and therefore they were released in the form of nuclear fuel debris, or nuclear fuel, so-called nuclear fuel particles. They were inside of these nuclear fuel particles. As a result of Chernobyl accident, a lot of radionuclides were released in the form of nuclear fuel particles. And here you can see the fuel particles in the Chernobyl fallout. These are electron microscope images of nuclear fuel particles. So dominant part of radionuclides deposited on the soil surface in the Chernobyl nuclear power plant vicinity was incorporated within this nuclear power plant. Fuel particles. Particles dissolution was the key process governing radionuclides mobility and bioavailability in soils during first years after the accident. Reliable prediction of the radiation situation dynamics in the Chernobyl area during these years was impossible without understanding and correct modeling of fuel particles behavior in soils and sediments. So it's time to say that before Chernobyl nuclear power plant accident, we never faced with fuel particles in the environment. Therefore, it was a really new scientific challenge to study the behavior of nuclear fuel particles in the environment. So, moreover, the release of fuel particles explained the differences of the behavior of different radionuclides on different parts of the trace after Chernobyl. Here you can see the comparison for cesium-137 of Chernobyl particles, Chernobyl origin. So, in case of 30 kilometer zone, only 20 to 30% of cesium-137 were in mobile forms, soluble or exchangeable. So, however, for longer distance, this fraction of mobile and bioavailable forms increased. For Bryansk region in Russia, it was already 40 to 60%, and in UK, in Cumbria, 85% of cesium-137 was in mobile bioavailable forms. And we can also compare these values with nuclear tests or global fallout, where more than 80% were in mobile form, and with Fukushima. So, if we are talking about the strontium in 30 kilometer zone, only 10 to 15% of strontium were in mobile bioavailable forms. In Europe, there was no strontium at all, because strontium was connected with fuel particles, and fuel particles are heavy and relatively large in size. They were deposited in the close vicinity of the Chernobyl nuclear power plant. In case of Kyshtym, we had actually liquid radioactive waste, and 80 to 90% of strontium-90 was in mobile bioavailable forms. The similar situation was for global fallout after nuclear tests. More than 90% of strontium-90 were in soluble forms. In case of Fukushima, there was no strontium-90 released. And generally, nuclear fuel was not released in case of Fukushima Daiichi nuclear power plant accident, fortunately. So, estimation of fuel particle dissolution rate. It's very convenient to use the strontium-90 speciation and its dynamics to estimate the dissolution rate. It has been shown that fuel particle dissolution in soils is satisfactorily described by the first order kinetics. Here you can see the equation for first order kinetics and the solution. And here you can see the air filter with fuel particles on the air filter. This is the image of so-called outer radiography. Okay, this is just explanation. So, but actually the main process of dissolution of fuel particles and their decomposition is oxidation of nuclear fuel, uranium dioxide, to uranium-3 oxide or intermediate intermediate oxide. uranium O2 plus X. So the point is that uranium-3 oxide is much more soluble as compared with uranium dioxide, with real nuclear fuel. And therefore, if we have fuel particles on the soil surface, so it's oxidized by the oxygen of atmospheric air, slowly, but still. And these particles leaves about the time scale of decomposition of fuel particles and its dissolution of radionuclides is about 2 years for soils. However, the situation is different for bottom sediments, especially for deep reservoirs. So the important water body in Chernobyl nuclear power plant is the cooling pond, which was used as a source of cooling water for Chernobyl nuclear power plant. And this water body has a depth up to 15 meters. And therefore, it is stratified and oxygen does not penetrate to the bottom. And fuel particles which were deposited to the bottom, they were somehow conserved over there for very long time because they were not oxidized by the oxygen. And so they were still there until recent time. However, recently, as you know, the Chernobyl nuclear power plant was completely shut down in 2001. And but Chernobyl cooling pond existed some longer time. But in 2014, the pumping from Pripyat River was stopped, and the level of water in the cooling pond decreased. Here you can see the result of this decrease of the level of water in the cooling pond. So a lot of bottom sediments started to be exposed to the air. And therefore, the fuel particles which existed in these bottom sediments, they started to be oxidized by the oxygen, and strontium started to be released from the fuel particles. And therefore, this caused some substantial increase of strontium concentration in the water of these water bodies. So, the main messages about Chernobyl. Chernobyl accident was the most severe accident in the history. Release of fuel particles as a result of the Chernobyl accident decreased radionuclide mobility and bioavailability, especially in near zone. So, fuel particles are important to be considered in spent fuel accidents and so on. And in this case, the experience from Chernobyl can be used for such modeling and calculations. Radionuclide wash-off and river transport are the most important process of post-accidental radionuclide special redistribution and secondary water contamination. Similar to Mayak area, dam reservoirs play a role of traps of radionuclides and contaminated sediments. Okay, now Fukushima accident, so which happened 11th March of 2011. First of all, this is the Fukushima Daiichi nuclear power plant before 2011. So the major reason for the accident was that 11th March of 2011, the Great East Japan earthquake happened. This was the most severe earthquake in the history, at least in the recorded history of Japan. So magnitude of 9 something. This earthquake triggered tsunami, very powerful tsunami, which caused Fukushima Daiichi nuclear power plant accident. Here you can see the picture illustrating the tsunami situation. Here, with the height 5.7 meter, is anti-tsunami wall, which was constructed by TEPCO. TEPCO is a company, private company, which was running Fukushima Daiichi nuclear power plant. So they decided that 5.7 meter is enough to prevent the water overflow and water penetration to the site. But the height of a tsunami wave was 15 meters on the site. So tsunami easily overcame this wall and flooded all the site of nuclear power plant. Of course, all the power lines to the Fukushima Daiichi nuclear power plant were destroyed even earlier by earthquake. So there was no power. But of course, in this situation, so nuclear power plant shut down automatically, and diesel generator started to operate. However, diesel generators were located on the knees of the building, and building was not hermetized properly. This means that diesel generator were broken with the water flood, and there was no power. And as a result, we had meltdown and hydrogen generation, hydrogen explosion, and this is the result of the accident. This is a picture soon after the accident, and the release of radioactivity in case of Fukushima Daiichi nuclear power plant lasted about 4 days something. And here you can see the trace which was established after the accident. So this is, I think this is the dose rate, but actually the similar picture is for cesium isotopes. But it is important that during these 4 days of release, the wind was mostly directed to the Pacific Ocean. Therefore, 80% of the radioactivity released as a result of Fukushima Daiichi nuclear power plant were transported to the Pacific Ocean, deposited there, and diluted. So Pacific Ocean didn't feel anything about it because the global fallout on Pacific Ocean was much more powerful than than Fukushima Daiichi nuclear power plant release, and therefore dilution of the release of Fukushima Daiichi nuclear power plant didn't increase substantially the levels of cesium concentration in the Pacific Ocean. Only local increase in the area adjacent to the nuclear power plant were increasing. So, these are again the hypothetical consideration of the spent fuel pools. The serious attention to this problem was initiated by Fukushima Daiichi nuclear power plant because each unit had its own spent fuel pool. And therefore, this pool is fed by the water all the time because there were problems. So people were concerned about these pools. And here you can see the results of some calculations for the accident of these spent fuel pools. Actually, in worst cases, the Tokyo with tens of million people, it was necessary to evacuate a lot of people, tens of million people, if such hypothetical accident would happen. This is another result of such modeling and calculation for the US. I think this is in Pennsylvania, Peach Bottom Nuclear Power Plant, and also in worst cases, you have very serious contamination. The red color corresponds to the more than 1 megabecquerel per square meter. This is very serious contamination requiring evacuation of the population. This is nevertheless the comparison of, let's say, contamination after Fukushima over here with contamination after Chernobyl. So you can see this is in the same scale, same spatial scale. So you can see that we have comparable levels, or sometimes even in the close vicinity to Fukushima Daiichi nuclear power plant, the levels of cesium-137 are higher than in 30-kilometer zone in some places, but still much smaller area. Of course, I told you already that 5 times less release of cesium isotopes happened in Fukushima, and moreover, 80% were transported away over the Pacific Ocean. Only 20% were deposited on the land after the Fukushima Daiichi accident. Okay, I told you about the fuel particles in case of Chernobyl. Soon after the Fukushima accident, also hot particles, so-called cesium balls, were identified and studied. So they have quite right shape like a circle or sphere. And here you can see the air filter. By the way, 170 kilometers away from Fukushima Daiichi nuclear power plant in Tsukuba, but on the first days after the accident. And these cesium balls are completely different from fuel particles. They don't contain any uranium dioxide, nuclear fuel, but they contain traces of reactor materials, including uranium, and even there was some information about finding of plutonium in these particles. But the main activity was because of cesium-137 and cesium-134. And in case of Kyshtym, we didn't have any hot particles, and mostly soluble radiocesium compounds were released. Okay, radiocesium in Fukushima, we found that is stronger bound to soil particles than Chernobyl-derived radiocesium. Its bioavailability for plants and aquatic biota is lower than in Chernobyl. So we think this is because of two reasons. First, highly selective sorption by clays and high fixation ability of Fukushima soils. So up to 30 and even higher percent of soil consist of clay minerals, which fix and selectively soak radiocesium. And the second reason is occurrence of these glassy hot particles in fallout. So, distinguishing feature of the climate of Japan in the area of Fukushima and Japan at all are typhoons or let's say tropical hurricanes. So here you can see one of them, Hagibis, which happened in 2019. And you can see here that in Fukushima, we had more than 400 millimeters per day of precipitation. I would say that Mayak for the whole year has only 400 millimeters. Here in Fukushima, we had 400 millimeters a day. So in Chernobyl, the annual precipitation is about 600 millimeters. So total annual precipitation in Fukushima is about 15 to 1800 millimeters. 2-3 times higher than in Chernobyl and even more higher than in Mayak. And therefore the self-purification, washout and so on is more intensive in Fukushima, and therefore natural attenuation is much faster. Here you can see the flood after this typhoon, and this is Abakuma River flowing through the Fukushima city. This is a picture nearby from my home. And important is that all rivers, they flow and end up in the Pacific Ocean. And here you can see what is important, that rivers have only 1 milligram per liter of potassium, which is the most important competitor, dissolving competitor for cesium. But ocean has up to 350 or even 400 milligram per liter of potassium. Therefore, there is a jump of distribution between solid and liquid phase of radiocesium. Radiocesium is seriously remobilized on the border between river and ocean. And this increase, of course, the cesium concentration temporarily for the coastal waters. Okay, main messages. Fukushima-derived radiocesium is stronger bound by soil and sediments particles as compared with Chernobyl, Mayak, and nuclear weapon test origin radiocesium. This promotes faster scavenging of radiocesium in surface waters and prevailing transport of radiocesium on suspended material with surface runoff and river flow. Higher precipitation in the Fukushima region, steep slopes at higher average air temperatures promote higher wash-off of radiocesium as compared to Mayak and Chernobyl cases, and faster natural attenuation of contaminated catchments. Extreme flood events during typhoons result in fast and efficient redistribution of radioactive contamination in Fukushima. Similar to Mayak and Chernobyl, dam reservoirs in Fukushima play important role of traps and prevent radiocesium transport downstream. So actually about three these cases, we have published this series of books with Springer. The series is called Behavior of Radionuclides in the Environment, and these 3 volumes devoted to Mayak first, Chernobyl second, and Fukushima. Here are the links for these books, and I thank you very much for your attention, and we'll be happy to answer your questions.
Thank you very much. Any questions?
Thank you for the very nice presentation. My question is towards these interesting hot balls of cesium. So what could be the reason that these were formed in one case for Japan, but not the other case?
Excuse me, can you speak louder?
Sorry. So my question is there any theory for these hot balls of cesium that they were formed in one case, but not in the other?
Yes, there is a theory of mobility and bioavailability of radiocesium. So first of all, particularly after Chernobyl, but also before Chernobyl, there were a lot of work on sorption-desorption of radiocesium on the solid phase. This is very important because this process is determining the concentration of radiocesium in solution. And radiocesium is taken by plant from soil solution, and therefore it is critically important to understand how it's distributed between solid and liquid phase. So it was realized that actually cesium is sorbed by soils and sediments very selectively because of several reasons. I will not explain it in detail, but it's important that cesium is strongly bound by a specific class of clay minerals, which is quite widely distributed over the world. So-called micaceous clay minerals. So they adsorb cesium very selectively. And only 2 cations can replace cesium on these sites, potassium and ammonium. And ammonium is 5 times more efficient than potassium. Therefore, it is important to control, first of all, potassium, of course, because this is the major cation, but also ammonium in water bodies, because in some cases, ammonium can reach quite high concentrations and not only compete with potassium for the desorption of cesium, but even prevail potassium. So another process is after this selective sorption, maybe I will show you here. Oh, not here. This is the mechanism of selective sorption. This is the, let's say, scheme of these micaceous clay minerals. So the cesium is sorbed on these sites because, why? Because cesium has very low hydration energy. Here you can see other cations which are, let's say, which have water molecules around. This is hydrated cations. But cesium has very low hydration energy, and it can lose these water molecules around and penetrate to this site and be sorbed. Moreover, steric characteristics of cesium cations are so that cesium fits very well with the size of these sites. However, this is a very dynamic situation. Why these edges are so-called fried? Because they have additional negative charge. From here should be potassium, but potassium goes away. And therefore, this layer have additional negative charge. This also, because they lost the potassium cations from here. So they started to do like this. But then potassium can return, and they go back. In this case, cesium, which is sorbed here, becomes fixed, non-exchangeable. It cannot penetrate over here. But the situation is dynamic. Then after some time, again, you can get this fried edge. And this process is called fixation. And this fixation is, the time scale of fixation is from several weeks to several months. It's slow, but still quite effective. Of course, sorption desorption is, the time scale of sorption desorption is, let's say, fraction of seconds. Okay, I hope I answer your question.
Thank you. Any more?
Thank you. Thank you very much for the presentation. So I have a question about the water treatment. Fortunately, I've seen the place before, and then so they have these huge containers where they store the water from after the earthquake, trying to process it. They use the ALPS treatment, and I've forgotten the full name, but ALPS treatment of the radioactive water. So they were saying if this treatment works, they are going to release it into the Pacific. And then some other countries had some reservations about that plan. So what's the current situation now? Are they still releasing it into the Pacific, or they found a way to solve it, like treat the water?
You are asking about the Fukushima, yeah?
Yes, yes.
Yeah, okay, yeah. In Fukushima case, so we have groundwater penetrating to the units, to the reactor, and this water contact with the nuclear fuel, and therefore the radionuclides transfer to this water. So we always have at the unit water, contaminated water, because the groundwater comes all the time. So again, I am not technologist, I am environmental chemist, but I can explain you how I understand the situation. So they pump the water, and if you take Google Earth and look at the Fukushima Daiichi nuclear power plant, you will see the whole site contains a lot of cylinders, tanks with contaminated and cleaned water. What's happening? So they pump the water to the tank, yeah? Then they clean the water from the radionuclides. How they do it? Actually, all radionuclides have specific sorbents which can catch the radionuclides. For cesium, this is hexacyanoferrate or Prussian blue, very effective sorbent. For strontium also. Actually, for all list of radionuclides, there are specific sorbents, and they use these sorbents to catch all the radionuclides from this contaminated water. And then they have more or less, let's say, cleaned or purified water. But what they cannot catch? They cannot catch tritium, because tritium is water. So I think it is possible in principle to separate tritium water from normal water, but this is very complicated and very expensive. So they still have tritium, which is more than permissible level in this purified water. Then they have a problem. What to do with this water? Because they have permanent process of pumping contaminated water, cleaning, and then they store purified water. So they decided they will discharge this purified water with tritium to Pacific Ocean. So they proposed this to IAEA. IAEA analyzed the situation. There was an expert group and so on. And then the IAEA said, okay. So, but this is not like, let's say, pipe which just discharged to the ocean. This is a pipe which goes quite far away to the ocean. Before that, there is a plant which dilutes this purified water by water until the levels lower with some additional value lower than permissible level. And then they organize the flow to the ocean for some time. This is not permanent. This is for some time to, let's say, to empty some tanks. This was started last year or year before, I don't know. And this lasts for several months, then stopped, but they intend to do it regularly because they need it. They need to, to to release it. What is my opinion? My opinion is there are many publications on the subject. There are many reports, including the IAEA and so on. So there are many sources over the world of tritium. So here, people concentrated because it's announced. But actually, many scientists consider that there is no threat from this. There is no threat, and there is no the probability of, let's say, any substantial concentration of tritium, which can damage anything, are not expected. Okay. Is it answered to your question? Yeah. Okay. Okay.
Thank you so much. I suppose there are no questions. Thank you one more time. And now we are going to have lunch. Please don't forget your tickets.